Right. Hello, everyone. My name is Evan Dewald. I'm a graduate student at Carnegie Mellon University. This talk is meant to be supplementary to my talk I just gave at SFF 2021. And so the application that we're talking about is Additive OS, which is an open source platform for AM data management and IP protection. Encourage you to check out the SFF talk if you haven't already. And this talk is really just meant to give a demo of how this application works and how you might use it in your own purposes. This is Additive OS. This is a browser-based application. It looks like a website, but it's really running locally on my machine through a Python client. I'm going to go ahead and log in. And first thing I want to do is navigate to this projects pane. And so this is where you'll be able to see a high-level overview of your different projects and also create new projects. So when I click create new project, I'll get this screen, which you'll see a few times. And what's happening here is the application wants to execute a function within this smart contract, this AM project smart contract, which is sort of underpinning everything and was gone into in a little bit more detail in the talk. Because anytime you add a transaction to a smart contract that involves updating this world state, such as adding a new project and initializing it in our contract, we have to sign that transaction using our Ethereum account and also pay a transaction fee associated with having someone verify that transaction, one of the nodes on the Ethereum network. So kind of the cardinal rule when it comes to managing an Ethereum wallet or any other cryptographic wallet is to make sure to keep your private keys secure and safe. So rather than having the application Additive OS, rather than having you hard code your private keys directly into the application or having Additive OS handle that directly, we've decoupled the transaction preparation step, which Additive OS does, from the actual transaction signing, which we're doing through a third-party browser extension called MetaMask. MetaMask is a popular browser extension, over 1 million users, and really robust to these sorts of workflows. So this is what MetaMask looks like. It's an independent from my application. You can see I can manage my accounts from different aspects of this Ethereum network. I'm using a test network where it's good for development purposes. And importantly, for my case, is these transactions will be free. So when I go to click sign transaction, it's Additive OS is going to request that MetaMask signs this transaction through my MetaMask wallet. I'm going to go ahead and I can manipulate the gas fees or the transaction fees that are associated with this signing this transaction. I'm going to go ahead and confirm this, and it's going to take a second while that transaction is added to the ledger. It's mined or it's added into an Ethereum block. And now I can see my new project that I've just initialized. I can go ahead and change the name of this. I'll call it Turbine Blade. I could go ahead and add users to this so that they can see it in their project panes as well and have access to add files and interact with it. You'll see different layers here. We have files, project files. We can also add post-processing and characterization data from this page. And then we'll talk about with these last two aspects of build ontologies and viewing the blockchain data. We'll talk about what those mean as we go along. First thing I want to do, as I talked about in the presentation, we want to add our Turbine Blade file, our verified approved file, to our smart contract. And as you see, we have the option always to choose not to add these files to our smart contract. It's not always necessary. And if you only use Additive OS as a data management system and not for the IP protection and security benefits, that's totally fine too. In this case, we're going to go ahead and select Add to Blockchain. I'm going to go ahead and select my STL file of my turbine blade, click Submit, and what's happening now is it's encrypting the file. We're encrypting that client side locally on the machine and uploading it to IPFS so that it can be accessed elsewhere. Again, you see this page where it's asking me to submit a transaction. Additive OS has prepared the transaction details based on that hash of the file you just added. And you see now we're trying to execute the add file smart contract function. Again, I'll connect to MetaMask and go ahead and sign this transaction. Same way, it'll take a second for that transaction to go through. Now I can go down and navigate to view blockchain data. We see that that transaction's still pending. These are executed asynchronously, so I can go about doing other things while I'm waiting for that transaction to occur. And when I refresh the page, I'll see that now I can link to Etherscan, which is an independent third-party website that really is just a way to read all the information stored on the Ethereum blockchain in kind of a user-friendly way. And so we can see a lot of information here. We can see the gas fees associated with this transaction. We can view the actual data that was sent with this transaction. You see there, that's our hash of our file. I can also go and view this contract itself, and I can skip over to the contracts page and actually view exactly what the code is that's executing these functions. If you have any doubt about what the function means or what exactly it's doing. So this add file function, for instance, is essentially just appending the file information, which is the checksum of that file and my Ethereum address as the one who executed the transaction, so that you can always verify who uploaded these files. And in addition to viewing the contract itself, I can see all the different transactions that have occurred and their timestamps, who was involved with them, and a lot of this is essentially that audit trace that can be independently verifiable. Even if my database falls apart, I'll always have the Ethereum ledger will persist, and you'll always be able to retrieve the most important information from there. And we see, there is obviously a database underneath Additive OS itself, so we can just make sure that this is the checksum being read directly from the database, and this is the checksum coming directly from that Ethereum transaction. So we just want to make sure that those match up. So next thing I want to talk about is getting more towards data management. Mentioned in the presentation that we're storing data within these spreadsheets. So we've developed these spreadsheet templates as part of a multi-university NASA University Leadership Initiative project, where we realize that we have a variety of different machines that all have slightly different conventions. It's not always easy to scrape the information directly from closed-sourced machine systems. And so what we came up with was these spreadsheets that store information about parts, infill parameters, contours, mostly the relevant input parameters, and then we can extend these as well to include heat treatments and post-processing, all sorts of things. But what I want to highlight here is that, as we talked about in the presentation, storing the data as directed acyclic graphs. And for a graph, we need some notion of direction and edges between two nodes. So we capture that within these spreadsheets as a naming convention. So Here we see the spreadsheet for build CMU03, and so the FID is the foreign ID, which is where we're coming from, and the UID is the unique identifier for this entry in the spreadsheet. So the convention here is build CMU03, and this is part, for instance, part 5 within this build. So the unique ID for this part is CMU03.05. And once we have that identifier, we can similarly sort of working our way down this build tree, we can now apply infill parameters to each of these parts or contour parameters. And similarly, so the infill parameters for CMU03.05 are CMU03.05.if. And this is a way to extend these spreadsheets, extend our graph representation through simply a naming convention. So what's stored within Additive OS is we import the data from these spreadsheets and then represent it in a NoSQL database that captures this build tree. So really what this looks like from a user perspective is just choosing the spreadsheet file type. We're not going to worry about adding to the blockchain. We saw how that worked. See spreadsheet not important yet. We'll see how that updates in a second once we add our spreadsheet. I'm going to go back and select my spreadsheet file. I can find it. There it is. So that's this is the spreadsheet file that you just saw. So now again, we're encrypting, uploading to IPFS, but we're also parsing the spreadsheet and importing it into the database. So now a couple of things have changed here. First, now we get this FID, if applicable, pane is now propagated with all the unique IDs from our spreadsheet. So not just the parts, but also the infill parameters, supports, and build overall. So sometimes you have acoustic data that captures the whole build, or build images that capture the whole build. We can capture micrographs. So let's say I have a micrograph of part CMU03.16, and I'll just show you that file. This is the micrograph that we're going to add. I'm going to go ahead and choose this file. I'm going to choose micrograph to specify the file type. Go ahead and submit, encrypt, upload, and in a second, we'll see that file associated here. Yep. And the other thing we did was assign this a unique ID, assign this file its own unique ID, which basically says that this is inheriting everything from CMU03.16. It's micrograph. We have a checksum, download, and remove if you need it. Also, what happened when I uploaded that spreadsheet is we got a build ontology tab here. And so this is going to redirect you to a visualization tool that includes everything stored on in that spreadsheet, visualized as our directed acyclic graph. So I can zoom in here. This is a pretty complex project. I can see my parts. These are infill parameters, and see all the data that's stored in our database. Of course, visualizing the data is great, but we can also export these graphs in a format that's compatible with PyTorch and TensorFlow, so that we can use graph neural networks to unlock these relationships. So we see parts. Here's our downscan parameters. Now, in the same way that adding a spreadsheet allowed me to associate files with a given FID, or like a part or a build, I can also get characterization data and post-processing information. So for instance, if now that part that I added a micrograph for, I want to add part density. Maybe this is something you extract from the micrographs, or you have tensile strength measurements, fatigue data. Now I can relate that process output information or mechanical properties to the inputs, which are reflected in these ontologies as well. So again, we can visualize that if I zoom in on part 16. I can move these around if you're interested as well. But now if I look at part 16, not only do I have the usual information that was stored in my spreadsheet, but that porosity percentage was associated now as well. And so this is how, with our neural networks especially, we'll be able to unlock these process structure property relationships and really bring it home to, for instance, predicting porosity based on all this other information. What other parts were in that build? Where were the parts positioned? And this is more than just a vanilla neural network where you have features and outputs. You have these relationships as well, which are at another feature that's just as powerful as the other features. And the other thing I can do now that I've uploaded that spreadsheet is go over to this Data Explorer pane. And this is, as a data scientist, you would probably be interested in querying this data and looking for unique relationships. So this is where you could try out these MongoDB-based queries and make sure that you're getting what you expect. So let's say, for instance, I want to query my database for parts that were built with a scan speed greater than 1800 millimeters per second. You can go ahead and test out that query, see that descendancy structure read directly from MongoDB, see all the information I would expect. And of course, this is a way to test things out, I would say, before you run the client in your programming language of choice. So MongoDB has extensions and drivers for Python, MATLAB, C++, JavaScript, Rust, tons of different programming languages. So as a data scientist, you don't have to compromise if you're trying to access this underlying data. So I talked about a second scenario in the presentation, a secure licensing scenario. And so this will work similarly to the projects pane, where I'm going to set up a new license. In this case, I'll add Greg at cmu.edu again. I'll add Greg's Ethereum wallet address, and this is not the private key. This is a public address. So this is safe to add, obviously. And so what this ensures is that my smart contract, in this case, will only let me add a new licensed print if that transaction is signed by one of these two wallet addresses. I'll go ahead. I'm going to just say one licensed print in this case, and we'll select that rotor blade file again. So the only thing that's happening in this case is Additive OS is going to only take the hash of this file. It doesn't need the file itself. Again, now we're on to the AM license smart contract, and we're doing the add license function. So it'll associate that metadata and initialize a new license where the number of prints is just one. So now I'll see that license ID pop up here. I can see the information. I can also see this Ethereum transaction, see that it's pending. So the next sequence of events would be adding a licensed print. So say you're the printer and you want to get a certificate of authenticity that is you can associate with that physical part. You would log the build report. I'm just going to use one of these files. Again, it's just taking the hash of that file. I will connect MetaMask and now execute the add print function. Sign this transaction. And now we see associated with license ID 2, we have 0 print licensings print licenses remaining. I can also download a QR code that now scanning this QR code will point you towards these transaction details. So this is Additive OS, the web-based application, but in just a few lines of code, you can also attach to these underlying APIs and build applications that run right on a Raspberry Pi, run on cloud servers to synchronize your IPFS pins and make sure that they're replicated and durable. I'm working on documentation for this so that you can run it yourselves. At this point, it will take a little bit of technical expertise as the administrator to set up Additive OS in your facility. But once you have it up and running, it's easy to add new users and allow them to connect their MetaMask wallets and get Additive OS running within your facility. So as I mentioned in the presentation, if you're interested in trying out this application, please let me know. Reach out to my email address. The documentation will be up very, very soon. And thank you for listening. I hope you enjoyed it.